Here we are given a graph of one of our toolkit functions and asked to write an equation for the function. The first thing that we want to do is decide which of our toolkit functions we are working with. We do this based on the shape of the graph. Because this is a V-shaped graph, this tells us that we are working with an absolute value function. So on my graph, I'm going to go ahead and sketch in my basic toolkit function just to have that as a comparison. So the absolute value of 0 is 0, of 1 is 1, and of 2 is 2. The absolute value of -1 is 1, and of -2 is 2. So normally our basic toolkit function would have the tip of the V right at the point 0, 0, and then would have a sharp V shape to it. So as we look at the graph that we were given, the first key point that I want to mark is that its tip of the V is now at the point -1, 2. So that means from our basic absolute value graph, it has shifted to the left 1 unit and it has shifted up 2 units. So left 1 and up 2 units. There also appears to be a vertical compression. A vertical compression makes our graph appear kind of wider. It's as if someone pushed the graph down towards the x-axis, and so the given V shape is wider than our absolute value toolkit function. So I can go ahead and fill into my function the format that would give me the shifts, and then we'll leave a place to come back and find that vertical compression. So I'm going to just leave a leading coefficient A in front for now, and we'll come back to that piece. So to cause our graph to shift left 1, this needs to change something on the inside of our function, and it feels a bit backwards. So to go left 1, we're going to put an x plus 1 on the inside. So for left and right, a plus shifts you to the left, a minus shifts you to the right. To cause our graph to go up 2, I'm going to put a plus 2 at the end. So outside of the function, a plus moves up and a minus moves down. So now we need to figure out the value of A, this leading coefficient that's caused the vertical compression. We know it's a positive value because we don't have any vertical reflection, and if it's a compression, it's a value in between 0 and 1, so some kind of fraction. So one way would be to just kind of look at some key points on the graph, but we're going to look at a strategy here that will also work for us as we get into more complicated functions later on. So I'm going to look for just some nice point on my graph. So other than that tip of the V, the kind of vertex, I notice that it goes through the point -5, 3. So -5 is an x value and 3 is a y value. I can plug this point into the equation that I've written and solve for A to find what my vertical compression value is going to be. So we have 3 equals A times the absolute value of -5 plus 1 plus 2. So -5 plus 1, we have the absolute value of -4. The absolute value of -4 is 4. So we have 3 equals 4A plus 2. So solving for A, I'm going to subtract 2 from both sides. So 1 is equal to 4A, and dividing A is equal to 1/4. So putting all of these together, we get that y equals 1/4 times the absolute value of x plus 1 plus 2. For any problem like this where you are given a graph and then you are asked to write the equation, we always want to do a check by taking a look at the graph on your calculator or on Desmos. So to do that, what you're going to do is you're going to take that equation that you just wrote and put that into your calculator or Desmos and take a look at the graph. Make sure that the graph on your calculator or Desmos matches the given graph. If they don't match, then we have an error in our equation. So anytime you are writing the equation, always take the time to do a check and actually graph that equation. Make sure that it matches the given graph.